Hey everyone, and welcome to This Explainer. Today, we're unlocking an absolute superpower, learning how to speak directly to a computer. We are going to explore the fundamental building blocks of computation using one of the most legendary, influential programming languages ever created, C. Honestly, think of learning C as learning the fundamental physics of software. Once you master these basic building blocks, you can build practically anything.
Here is our blueprint for today. We're going to cover the foundations of programming, set up our workshop, dive into structure and data types, look at input, output, and math, learn about making decisions with code, and finish up with the power of loops. Let's get into it.
All right, Section 1. Foundations of Programming. Let's tackle that fascinating space between human thought and machine processing.
So I want you to think about this. How exactly do we translate our abstract, messy human intentions into specific actions that a machine of silicon and electricity can actually execute? I mean, computers are lightning fast, but they're incredibly literal. They need a bridge, and that's exactly what programming languages are.
But, before we even touch a keyboard, we need a plan. Enter the algorithm. Think of it as a logical recipe. It's just a step-by-step procedure designed to solve a very specific problem. And it has to have three things: clarity, so there's zero confusion; finiteness, meaning it eventually finishes; and effectiveness, meaning it actually solves the problem. And the cool part, algorithms don't care about software or hardware. You could literally write one out on a napkin. This brings us to a super important distinction. The algorithm is the human logic. It's written in plain language designed for our brains to process. But a program, that's the strict machine-level implementation of that algorithm, written in a specific language, like C. It's strictly for the computer to execute, and it relies entirely on translation software to actually do anything. Moving right along to Section 2, setting up the workshop. Just like a carpenter needs tools, we need a digital space to build code. Since computers basically just speak binary, ones and zeros, our high-level C code has to be translated. There are two main ways to handle this. Compilers, like GCC, translate the whole program at once before it ever runs. That makes the final program super fast. Interpreters, on the other hand, translate line by line while running, which is great for debugging but a bit slower. For C, we are firmly in the compiler world. So how does that compiler process actually work? It's a strict 5-step journey. Step 1 is our human-written source code file ending in .c. Step 2 is pre-processing. This strips out our notes and handles initial setup. Step 3 is the actual compilation, converting our code into raw object code and checking for typos. Step 4 is linking, which connects our code to necessary system libraries. And finally, Step 5 gives us our executable program, ready to run at lightning speed. Okay, Section 3, structure and data types. Time to lay the foundation and look at our raw materials. Check out the elegant anatomy of a C program. Right at the top, we almost always have preprocessor directives, those lines starting with a hashtag. It's basically telling the compiler, hey, go grab the standard input and output tools before we do anything else. But the absolute star of the show is int main. This is the entry point. Whenever you run a C program, the computer immediately looks for this main function and runs whatever is inside those curly braces, usually wrapping up with a return 0 to say, hey, everything went great. Inside that main function, we need places to stash our data. We use primitive data types, which are basically little storage boxes. We use int for whole numbers, like your age, float for standard decimals, like a price tag. If you need a massive, super precise decimal, you step up to a double. And to store just a single letter or symbol, that's a char. By defining these specific boxes, our program runs incredibly efficiently and safely. Next up, Section 4. Input, output, and math. Our structure is built. Now let's get things wired up to the outside world. Code isn't much fun if it totally ignores the user, right? We spit out text using the printf function, but to actually grab user data, we use scanf. You'll notice a %d in quotes. That's a format specifier expecting an integer from the keyboard. But the real trick here is that little ampersand sign right before the variable name. That's the address operator. Scanf needs to know the exact memory address in RAM so it knows precisely where to shove that incoming data. Now, what happens if you try to mix a whole number and a decimal in an equation? Well, C handles this in two ways. Implicit conversion is completely automatic. The compiler just quietly upgrades the integer to a float behind the scenes so the math works. But sometimes you need to take the wheel. Explicit conversion, or typecasting, is when you manually force a variable to change types in that moment, like deliberately chopping off a decimal to force a number to be whole.
All right, Section 5, making decisions with code. At this point, we just have a calculator. Let's give our program a brain.
This is where code actually gets smart. The if-else structure lets our program fork down completely different paths based on a logical test. It basically asks, is this condition true? If yes, it runs the first chunk of code. If no, the else kicks in and runs a different chunk. And you can chain these together with else if to handle totally complex, multi-layered scenarios. It's quite literally a choose-your-own-adventure book for your computer. To make those decisions really robust, we use logical operators. Think of these as the brain's synapses. If you need two completely separate things to be true at the exact same time, you use the AND operator. That's 2 ampersands. If you only care that just one of a few conditions is true, you use the OR operator, the 2 vertical pipes. And if you just want to check if something is simply false, hit it with the NOT operator, which is just an exclamation mark to flip the logic entirely. Finally, Section 6, the power of loops. Time to fire up the true automation engine of our code. Honestly, without loops, a computer is just an overpowered abacus. Loops are where the real magic happens. They are iterative control structures that tirelessly repeat a set of instructions. We're talking millions of times a second, as long as a specific condition holds true. They're absolutely essential when you're chewing through massive amounts of data and don't know exactly how many steps it'll take beforehand. C gives us a couple of flavors here. A while loop checks its condition first. If it's true, it runs. But if it's false right out of the gate, it might never run at all. A do-while loop, on the other hand, totally flips the script. It blindly runs the code block first and then checks the condition at the end. So you are absolutely guaranteed it's going to execute at least once, no matter what. And that brings us to what is arguably the most elegant tool in the whole language, the for loop. You use this when you know exactly how many times you need to repeat a task. It is amazingly compact. Right there in the parentheses, you have your initialization, where you start counting, your condition, when to stop, and your update, how to count up each time. It bundles all that control into one single powerful line, leaving the curly braces purely for the action you want to repeat. And there we have it. We've gone all the way from the abstract theory of human algorithms down to the structural reality of loops, variables, and logic gates in C. You now possess the absolute building blocks of computation. Your digital workshop is humming, the tools are in your hands, and the compiler is ready. So, now that you know how to actually talk to the machine, what real-world problem are you going to automate first? Thanks for joining me on this explainer, and keep on building.